My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. So hope you are well and safe from Corona pandemic. So we are trying to adjust with this new normal situation. So and we have successfully completed our 120th International Physics webinar. And today it's our 121st International Physics webinar. And I think you have already come to know that we have arranged a series of webinars. In those webinars, physicists from different countries are coming as a main speaker. They are sharing their knowledge with our student and they're delivering their speech. And I think by this way, our students are benefited. And in those speakers, two of them are Nobel laureates. So we are very lucky for having those professor with us. So today is a very important day for our department. Today I'd like to welcome to our to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Astronomy, Yale University, USA, in physics. And we have with us here today Dr. Sarbani Basu, Madam, Professor and Chair, Department of Astronomy, Yale University, and she has already connected with us. So I'd like to welcome our speaker. So, Madam, namaskar, and welcome to our International Physics webinar. আপনাকে স্বাগতম যেহেতু আপনি বাঙালি এজন্য বাংলায় বললাম তো it's our honor and privilege to host you in our International Physics webinar, madam, and we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation in this corona pandemic situation. So for those who are new, I'd like to introduce that we have divided our webinar into three parts. First of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver her speech with you, and at the end we have a discussion time. In that time anybody can join with us, and you can ask question by commenting also. So I think you have come to know the title of this today's International Physics webinar, and title is The Mysteries of the Sun, and our speaker is Dr. Sarbani Basu, Madam, Professor and Chair, Department of Astronomy, Yale University, USA. And you can see her professional career and educational career. Dr. Sarbani Basu, Madam, is a professor in the Department of Astronomy, Yale University, and its current chair, Professor Basu, is an astrophysicist who studies the sun and other stars using the technique of helioseismology and astroseismology. She is a fellow of the American Association for the Advancement of Science and is the vice chair of the board of the directors of the Association of Universities for Research in Astronomy. She is a fellow of the American Association for the Advancement of Science and American Astronomical Society. Professor Basu is an expert in the use of helio and astroseismic techniques to study the structure of and dynamics of sun and other stars. Among her achievements, if the characterization of the density and temperature distribution of the solar interior, characterization of solar rotation, and also the study of solar abundances, in particular the abundances of helium in the sun. Professor Basu also studies the changes that take place in the sun over time scale can affect human society. She uses data from Global Oscillation Network Group, Birmingham Solar Oscillation Network, and the Michelson Doppler imager on board SOHO, and the helioseismic and magnetic imager on the Solar Dynamic Observatory. Professor Basu's research interests including trying to put the sun in the context of the other stars, and to end she does astroseismic analysis of other stars with data obtained from the NASA's Kepler's and Chase mission. We can see her educational professional preparation. She completed her bachelor degree in physics from Women's Christian College, Chennai, India, and MSc from the University of Pune, India, and PhD Tata Institute of Fundamental Research. And she also done two postdoc, one from Queen Mary Westfield College, London, and another from Theoretical Astrophysics Center, University of Arches, and also member Institute for Advanced Study, Princeton, USA. We can see her honors and award. You can see, and the scientific organization committee and meeting, and research interests: exoplanets, solar and stellar astrophysics, astroseismology, helioseismology, solar structure dynamics activities, stellar population. And you can see Google Scholar ID, and her citation number is more than 29,000. So this is her books, he has written, she has written. So thanks for your patience. Now it's time to our go to our speaker. So thanks again, madam. You can start your session. It's your time, madam.
Thank you, Professor Dash, for the kind
It's my
invitation
pleasure.
and the kind introduction. I would like to take this time to talk to you about our nearest star, so the Sun. Most people forget in day to day life that it is a star. And of course, unlike other stars, the Sun means a lot more to us because it is the ultimate giver of life. We would think that we know enough about the Sun, but it turns out that a lot of the issues of the behavior of the Sun that takes place on time scales that affect us, uh, they are still quite unknown. We don't know many of the reasons why things happen the way they happen. So let me go through you some of the stuff that we know and then in the process tell you what we do not know. Okay. So let's take a look at the Sun. We know its radius quite well. It's 6.9599 times 10 to the 5 kilometers, or roughly 700 megameters. That's a nicer number to remember. It is approximately 2 times 10 to the 30 kilograms. I have written the number in grams because astrophysicists, for some reason, stick to CGS units rather than MKS units. If you look at the composition of the Sun, the outer parts of the Sun is composed of 24% is helium, roughly 74% hydrogen, and 2% of everything else. So by everything else, I mean nitrogen and oxygen and iron and every metal that you can think of. Now, this is just in the outer layers. The core of the Sun, where nuclear fusion occurs and produces energy, there the hydrogen amount is decreased substantially because the Sun is a middle-aged star. So in the core, we have about 33-ish% of hydrogen. The surface temperature is roughly approximately 6,000 Kelvin. It's what in astrophysics is known as a cool star. Yes, it's very hot, but there are much hotter stars. And the Sun is roughly 4.5 billion years old. And it's, as I said, middle aged in the sense it'll live another about 5 billion years before it exhausts hydrogen in the core. Now, stars like the Sun are actually. Is this slide visible? Okay. Thank you. Stars like the
Yeah,
Sun
maybe
affect.
there is a, excuse madam, there may be a problem in the slide.
Yes, there
Okay.
seems to be an issue. Ah,
And now it's okay,
let.
madam.
Okay, good. Thank you.
I think, but no,
Um,
no, no, no. It's still the problem.
let's. Should I? Let me get off
Stop
the
share
screen.
and yeah,
Yeah.
do it again.
No, why don't I just keep it this way? This is clear, isn't it?
Not yet.
For some reason, no. For some reason,
I
it.
think could you stop the PowerPoint and open it and share it again? I think it will work.
I'm actually sharing my whole screen.
Okay, okay.
Maybe that's the issue.
Just
Let's let's get out of this. Uh, okay, what happened to my? Yeah, these technical issues. They are okay. You can see this now.
yeah, we can.
Okay, let me stop share and start sharing
Mm,
it.
yeah.
Okay, share screen. No. funny. Sorry. It doesn't even. What do I want to do? I want this. Can you?
You can see.
Okay, you can see this, but you can't see my cursor this way. Unfortunately, let's take another look. I do apologize for the. Huh. No, it doesn't like that. So I think I still have to share my entire screen for some reason, but okay. It's a slideshow thing which is giving a problem. So what I'm
Yeah,
going to do is I'm going to just do it
just like,
this way.
yeah,
This way should
okay,
be okay.
that could be better.
Yes.
Okay.
And I can actually make this smaller so that you can see a bigger screen. I think this should work. Apologize, but technology sometimes fails
Yeah,
us.
it's okay.
So, so stars like the sun are actually quite easy to model. The structure of the stars like the sun, because they're mainly spherically symmetric, which means their internal structure is only a function of radius and not latitude or longitude, which means that we can express the properties, even though it's a three-dimensional object, we can express the properties in one dimension, i.e. radius. So we get a set of one-dimensional equations, which is so much easier and quicker to solve. So the equations, I'm not going to go through the equations, but just to know, they're actually fairly simple equations. There's a conservation of mass, conservation of momentum, thermal equilibrium, which basically implies that whatever energy you're producing inside has to be radiated away, otherwise the star will puff up. Transport of energy, because after all, we have to transport the energy from the interior to the exterior. And transport of energy in stars like the sun happen through convection and radiation. Conduction is of no importance. But to do so, and we need some inputs like opacities. Opacities quantify how opaque stellar material is to radiation. We need nuclear reaction rates. We need to figure out what are the different processes through which abundances change. For example, in the case of fusion, hydrogen is being converted to helium. So that's a change of abundance. And we need the equation of state. So what is the relation between pressure, density, abundance, and temperature? The equation of state is a fundamental property. It's not something we can just assume. So for example, we're all used to the ideal gas equation of state. But while ideal gas is a good approximation for stellar material, it is only an approximation, doesn't work very well. So the quantities on my screen in this green color are the one which other atomic physicists calculate for us, for astrophysicists, and we use in our models. So what is the opacity? What is how fast do nuclear reactions occur at a given temperature and density? And what is the equation of state? Once we make a model like that, okay, in the case of the sun, it's a bit different from other stars because we know a lot more about the sun. We have an independent constraint on the age, which is obtained through radioactive dating of old meteors. We know how bright the sun is, the luminosity, and we know the radius of the sun. There are free parameters in the modeling process, which we play with till we get a good model. How good the model is depends on the physics inputs and the processes. And a bit later in the talk, I'll show you how good our models actually are. But once you model the sun, what we find, this is just a schematic structure of the sun. The core of the sun, where nuclear reactions are occurring, is at about 15 million Kelvin. The inner 30% of the sun, energy is transported from the core to this layer, which is marked in orange, by radiation, that is by the movement of photons. The outer 30% by radius is convective heat transport, so boiling gas. And we know the position of this interface very, very well because of helioseismology. It's at 0.713 plus or minus 0.001 solar radius. So it's a big test of how good our solar models are. Now, we don't have to just rely on theory to know that this outer part is convection, because if we look at the sun, we see the convective cells. This is one of the highest resolution images of the surface of the sun. It's the first light image of the new solar telescope called the Daniel K. Inouye Solar Telescope. Each of these cells is, it's pretty big. In the US, we would say each of these cells is of the size of Texas, which is slightly bigger than Bangladesh, I believe. And of course, because these are convective cells, they move. This is, you can see the convective cells moving. So the cells rise and they fall, the material rises and falls. And I'll tell you at the very beginning, convection is very difficult to model in stars. It's one of the biggest sources of uncertainty in stellar models. Okay. So what is the problem that we have? Well, our models give us an incomplete picture. Our models tell us roughly, actually not roughly, quite well, what is the behavior of a star over stellar evolutionary timescales? That's timescales of millions to billions of years. It does not give us a complete picture of the structure of the outer layers, some of the inner layers, or what is going to happen, say, in 10 years' time. So I'll start by looking at some of the problems one by one. One is the temperature gradient, okay? So this here is the surface of the sun, and this is the temperature, the dark line, as you go away from the surface. Now you can see there's an issue here because the source of energy is somewhere at the core of the sun. So you expect as you go away from the source of energy, the temperature should keep decreasing and decreasing and decreasing. Instead, there's a minimum, and then the temperature sharply increases, and the temperature of the very outer layers, about slightly more than 1,000 kilometers out over the surface of the sun, is 2 million Kelvin. One of the big problems, which we think now we have a solution to, and it's a recent solution, is how does this part get so hot if the energy source is down here, okay, and it's cooler at the surface? So these colored lines just show in what wavelength band we can actually look at these regions of the star. So if you want to look at the solar corona, which is the highest temperature region, you look in ionized iron lines, for example. Okay. Another mystery is the fact that the so-called solar constant, which is the amount of solar energy that we get at Earth per square meter, is not a constant. It shows an up and down periodic variation. And this periodic variation actually follows the periodic variation of the number of sunspots. So what's a sunspot? I beg your pardon, I shouldn't have done that. Okay, sunspots are these dark spots that appear and disappear on the surface of the sun. They were first discovered by Galileo and caused quite a stir because the heavenly bodies were supposed to be perfect and not have blemishes. Sunspots, of course, are more than just dark spots, and this is the highest resolution image of a sunspot taken to date. Again, it's been taken by the Daniel K. Inouye Solar Telescope, and you can see, I mean, it's like a sunflower. Beautiful. The structure is caused by magnetic fields, and schematically, what happens is you have a bunch of magnetic field lines from the interior, they cross the surface, and then because you can't have magnetic monopoles, they go back into the surface. The footprints are sunspots. We know these are magnetic regions because, of course, we can actually take magnetic images of the sun, so-called magnetograms. So these two are just showing the magnetic structure of the sun. These two are magnetograms taken by two different instruments. The HMI instrument is a successor of the MDI instrument and has a higher resolution, so you can see more detail. But what you can see is that there's magnetic field all over the sun and very strong magnetic fields. The color bar tells you how strong. Again, sorry, we don't generally use Tesla in astronomy. We use kilogauss and Gauss. So this is the structure of an active of a sunspot in magnetic fields, and we just call them active regions because the sunspot is probably generally smaller than an active region. Now you see that there are magnetic fields spread out all over the surface. It's known as the magnetic carpet. So the green and white image and the black dots, that's an image, a sort of processed image from the SOHO satellite, one of the instruments on the SOHO satellite. And the white points, white and black points, are sort of small magnetic regions that cover the entire sun. And these white and black lines here are illustrations of the magnetic field lines that join these magnetic footprints. And it is this magnetic carpet which probably transports energy from the surface of the sun to the outer layers, making the outer layers so hot. Okay. Now, can a magnetic carpet actually exist? Can we simulate that? It turns out magnetohydrodynamic simulations for conditions at the solar surface easily gives rise to a magnetic carpet. So this is a rendering from a simulation by Irina Kitiashvili and Alan Ray from NASA Ames. And yeah, they can roughly, I mean, this is not quantitatively the same as what is seen, but qualitatively it is the same. So you do see magnetic field lines in a magnetic carpet, and we believe this is what actually heats up. But again, it's not a fully solved mystery. Now, magnetic regions, so sunspots, actually look very different if you look at different layers of the sun. So this lowermost part is what we see. This is the photosphere. Okay, this is the surface of the sun as we see it. If we go above, the different color images are at different wavelengths. Okay. As you keep going up, the structure reveals complexity and the magnetic field lines. You can actually, once you go to the corona, you can see how the magnetic field lines look like. And one of my favorite images is one from NASA, where we see the sun at the same point of time in different wavelengths. So this is a Dopplergram where you look at the velocity of different layers of the surface. This is a magnetogram, so you can see this active region. But if you saw by eye, you won't see this huge structure, and you won't see this at all, because this is roughly what you'll see if you looked at the sun with your eye. You'll see the sunspots here, but nothing corresponding to this. But as you look at different wavelengths, you see the amazing complexity of the structure. And it's not completely understood how the connectivity between different layers, because that would require a simulation with a huge dynamic range. And to my knowledge, that hasn't been done. We do use sort of pencil and paper analytic calculations to show that this is how things are expected to behave. But the radiative conditions for every wavelength, that hasn't been quite solved in detail. Okay. So I talked about the solar constant not being constant following the sunspot cycle. This is basically what we call the solar cycle. So I have time on my x-axis, number of sunspots on my y-axis, and you can see that the number of sunspots rise and fall and rise and fall. This is what people call the solar cycle, sometimes the magnetic cycle, sometimes the solar activity cycle, same thing. We are here. No, sorry, we are actually here. So this is slightly outdated. This cycle here is cycle number 23. People started numbering them from somewhere here. We have just begun cycle number 25. Okay. But it's not just the number of sunspots that rise and fall. Where the sunspot occurs at each cycle depends on the phase of the cycle. So at the beginning of the cycle, the sunspots occur at fairly high latitudes. Well, 30 degrees is not high, it's intermediate latitude. And as the cycle progresses, they occur at lower and lower and lower and lower latitudes till the next cycle begins, when they jump back to a higher latitude. And there is often an asymmetry between the northern hemisphere of the sun and the southern hemisphere of the sun. What the upper panel is showing is the area covered by sunspots. Okay, so this diagram, because these look like wings of a butterfly, is known as a butterfly diagram. And what's shown in the lower is just the average area per day. So the peaks are the solar maxima, the maximum of the cycle. The troughs are the solar minima. We have just begun solar cycle 25. Okay, so this corresponds to, of course, magnetic fields. And this, instead of just a plot of sunspot area, these are magnetograms. This is a time average zonal, a longitudinally average magnetic diagram. The yellow and the blue are different polarities. And you can see the butterfly diagram in this diagram. Sunspots occur in this spot. So the question is, you see these magnetic flows, magnetic features going from the intermediate latitudes to the high latitudes. Why do sunspots occur here and not there? We don't quite know, but we know that these poleward flows are crucial for the beginning of the next cycle. And you can see this is cycle 24. Cycle 24 was very weak. And you can see that in the northern hemisphere, the poleward flow is very, very weak. So here it was very strong. And also the one thing you can see is that at each hemisphere, the polarity, the major polarity of the sunspots change with cycle. So in one cycle, you can see the yellow, then the blue, then back to the yellow, back to the blue. So in cycle 25, the northern hemisphere will be mainly positive, so the yellow. Now, just for a pretty picture, this was a recent NASA and ESA image showing the sun at the same month from 1996 to 2020. 1996 was solar minimum, very few sunspots. This is an image of the corona, so 2 million Kelvin. 2001, you can see, is very active. That's the solar maximum. We go down to solar minimum in 2009, solar up to solar maximum again in 2015. Then we had solar minimum 2019, December 2019 is, I think, what people believe is the solar minimum. And this was in 2020, this was one of the first sunspots of solar cycle 25. The reason we bother, at least many people bother about the sunspot cycle, is that strong active regions give rise to mass emissions that can reach the Earth, can perturb the Earth's magnetosphere, and actually cause problems, particularly with technology. The first such issue was in 1859 when there was a massive event. We call it the Carrington event because Carrington was one of the first people to see it and study it. The charged particles from the sun affected the Earth's magnetic field. They got into normally the charged particles are repelled by the Earth's magnetic field, except towards the magnetic poles where we see them as aurora. But these were so powerful that they penetrated the Earth's magnetic field. Those were the 1859, there weren't too many power lines around, but there was telegraph. That was the highest technology of the time. And telegraph wires were overloaded, and telegraph operators got shocks when they tried to use their equipment. Today, if we had a Carrington event, it would cause trillions and trillions of dollars in damage to technology mainly, because satellites, all the communication satellites, GPS, our power infrastructure, transformers, they could easily be killed. So we really need to know how to predict these. At the moment, there is no way to predict these. So what we do is there's a satellite called SOHO, which is at the L1 Lagrange point between the Earth and the Sun. That's the point where the gravitational forces of the Earth and the Sun are equal. Since it's about 3 times as far away from the Earth as the Moon is, it can give us a sort of warning, because it will see the charged particles before they come to Earth. It sends a signal back to Earth. Signal is, of course, through electromagnetic means, which is faster than charged particles. So you can get 30 to 45 minutes of warning to shut down systems. But that's not really, that's a solution, but we would like to be able to predict when these things happen. The problem is, forget about predicting these eruptive events from these large sunspots. We are currently not even capable of predicting the strength of a solar cycle. So before solar cycle 24, which is the cycle that ended, NASA put in a call to various scientists to try and predict what is going to be the maximum number of sunspots on the sun during the maximum of cycle 24. All these colored bars, these are the predictions. The dashed and dot dashed line, they're sort of the 2 different averages. What really happened was this blue line that I have drawn. So you can see that most predictions were wrong. Some predictions got the number right, but we do not know if that is by chance or was the physics in the models better. We will know that in cycle 25 because NASA did exactly the same exercise. Well, cycle 25 maximum is still 5 or 6 years away, so we have to be patient. One of the things about studying sunspots is, if you're studying current sunspots, is there's no way for us to hurry it. You have to be patient. That image that I had shown earlier, this basically encompasses my professional astronomy career. This is only 2 solar cycles of data. And I'm hoping I'll be able to see all the end of cycle 25, but let's see what happens. Okay. So that's a problem, as I said. We want to see which of these predictions is going to be correct. And if the predictions that are correct for cycle 24 also predict correctly for cycle 25, because that'll be an indicator that whatever they have in their models to predict the next cycle is roughly correct. So what else can we do? So what I try to do is, okay, solar cycle, whatever is causing the change of solar cycle, is taking place inside the sun. So why don't I try to see, using helioseismology, which is seismology of the sun, A, what does the solar interior look like? And B, well, we see a solar cycle outside. Do we see changes inside the sun that show a dependence on magnetic activity? The sort of magnetic activity that we see at the surface, okay? Now, just a very brief introduction to helioseismology. So we're all used to seismologists on Earth. They study earthquakes. You have an earthquake. Somewhere here, there are seismic stations elsewhere. They see how long the signal takes to reach there. And by looking at the type of signal they see, and how long it takes to get there, they figure out what's the structure of the earth is, okay, what's happening inside the earth. We don't do that for stars, because for stars, we can do, we use normal modes. So we are used to normal modes in strings. So if you have a string, any of you who've played a stringed instrument, you know you pluck the string and the string gives out a characteristic frequency. So if you have a string attached at 2 places, you have the fundamental mode, the first overtone, the second overtone. This is in 1D. Stars are 3D objects. In 2D, think of a drum, okay? Or if you're in India or Bangladesh, think of a tabla, for example. There, it's a 2D object. The membrane is two-dimensional. So you have nodes along the circumference, and you can have nodes along a radius. So you need 2 numbers to denote the mode. So these are sort of modes of a vibrating drum. These are Bessel functions. In 3D, you not only have the surface that is distorting, but you'll also have the interior distorting. So you're going to need 3 numbers. So the sun is a 3-dimensional object. So each mode is characterized on the surface by an angular eigenfunction, eigenvalue. These are just the spherical harmonics. So if you remember your hydrogen wave function from quantum mechanics, we use the same thing. It's just that the radial wave number is different. So these modes come in many, many, many different frequencies, and the frequencies are what we use to figure out what's going on inside the sun. So what would the observations look like? This is a processed Dopplergram from showing solar oscillations. So of course, this image itself or this movie itself is not useful. What we do is we extract the individual mode frequencies from this mess and use those to figure out what is going on inside the sun. Why can we do that? Different modes travel to different parts of the sun or of any star. Some modes only sample the shallower layers, some modes sample the very deeper layers. So what we can do is we take a model, we look at the frequencies of these different modes, look at the differences in frequencies between the model and the sun, and figure out what is the difference in structure between the model and the sun. This is often known as helioseismic inversions. So, what do we see? If you recall, I had made a statement that we can actually model the structure of the sun quite well. And this is how we know it. What I'm showing in this figure, on the x-axis is the interior relative radius. So this is the core. This is the surface. In this figure, the y-axis is the relative difference between the squared sound speed squared, between the sun and one of our models. So we have two different models here with slightly different physics. Note that the biggest difference is only 0.7%. In most of astrophysics, we would say, yay, we have a perfect model. However, you also see the error bars here. So it may be only 0.7%, but this is a very, very significant difference. The graph on the right is density. Okay. Now, even though this is a significant difference, I still say we can model the interior well because we know why this difference is occurring. This is mainly because in our models, there is no mixing of material below the base of the convection zone where energy is being transported by convection. In the sun, there is evidence that there is mixing taking place there. If you mix it, if you have a model with that sort of mixing, this will go away. Okay. Now, so we are pretty sure we know the structure very well. Okay. Dynamics, not so much. So observations had shown that the solar equator rotates faster than the poles. So using that data as fluid analysis, predicted that if you could take a slice of the sun, you would see that the different layers of the sun rotate on cylinders, meaning the isorotation contours would be parallel to the rotation axis. So for example, if you have one cylinder, another cylinder, so these isorotation contours are parallel to the rotation axis, okay? What we see instead is this. The isorotation contours are not parallel to the rotation axis. They're almost radial in the convection zone. This black line denotes the base of the convection zone. You can see that the equator is much faster than the poles. The color bar is in nanohertz. That's the units we use, but roughly the equator rotates once every 25-ish days, the poles more than 30 days, okay? So this does not look anything like this. What we notice is two things. One, at the base of the convection zone, there's a sudden shift in the nature of the rotation. It's almost solid body-like beyond in the deep interior. And there is, closer to the surface, a change again in the nature. So this is what we call the near surface shear layer. I shall show it this way. So I'm showing the same thing, but I'm taking cuts at different latitudes. So the black is the equator. Equator blue is 30 degrees. This is 45 degrees, 60 degrees, and I think this is 80 something degrees. There are two places to note. One is this change at the base of the convection zone. We call this the tachocline. And this is where we believe that the magnetic fields in the sun are generated. Magnetic fields are buoyant in a convection zone, so it's going to be hard to keep them and make them stronger in a convection zone. But this interface region, you can see with the rotation rate changing so much between the convection zone and the interior, you have a lot of shear there. So you could generate magnetic fields. And there's also this change very close to the surface. So the surface rotation is not the fastest. The fastest rotation is slightly deeper. This we call just the near surface shear layer. Well, very unimaginative. We don't completely understand the role of that. But the tachocline is where we believe that the solar magnetic fields are generated. Okay. We also see, if we remove the average solar rotation, we see bands of prograde and retrograde flows. These are known as zonal flows, and I'll come back to zonal flows because these show solar cycle related changes. And in addition, what we find is there are flows from the solar equator to the poles. So in the northern hemisphere, so red is positive velocity, means to the north, blue is negative velocity to the south. So in the northern hemisphere, flows go from the equator to the north, towards the North Pole, in the southern hemisphere from the equator to the South Pole. Meridional flows also show a change with time, and we believe these are the flows that are responsible for taking the magnetic fields from the equator to the pole, where it somehow goes down to the interior and gets recycled for the next solar cycle. Now, helioseismic frequencies change with time. And this is a graph where we show frequency differences as a function of time. Please don't bother about the details, just to show that if you plotted frequency differences, take the frequency of solar minimum and find the difference of every other period frequencies at any other time with respect to that, it follows the same up and down as the solar cycle, which means there's something happening to change the frequencies. Okay. So what do these changes imply? Okay. The most interesting part is, because we're talking about magnetic activity, which you need to generate through a shear or something, the average rotational rate across cycles 23 and 24 have been different. So cycle 23 was the first solar cycle for which we had detailed helioseismic data. We had found what happens during a solar cycle with cycle 23 data and expected to see something very similar in cycle 24. We do see something similar, but there are also differences which we do not understand. So we know now, after having two cycles of data, that the average rotation rate for the two solar cycles have been different. Perhaps that's not surprising. The average magnetic activity of the two solar cycles were different. Now, we also know that solar zonal flows change with time. Recall that the zonal flows are these banded flows. So what helioseismic data have shown is that the zonal flows are not restricted to the surface. They go quite deep, and that the latitudinal structure changes with depth. So for example, this red bit here is a prograde band, which at the surface is at one latitude, because this is equator, that is the pole. but deeper interior is at a different latitude. And each of these panels is at a different time. Okay. This is not a very good way of looking at the data. So what we normally do is take a depth. So this is at 0.98 solar radius, so just below the surface, and plot the flows as a function of time and a function of latitude. This white band denotes is the time where when cycle 23 ended and cycle 24 began. Note one thing, the velocities of these zonal flows were much stronger in cycle 23 than in cycle 24. If you remember the magnetic field butterfly diagram that I had shown earlier, there the poleward magnetic fields were stronger in cycle 23 and very weak in cycle 24. It wasn't just the magnetic field, the flows are also weaker. But perhaps one of the more interesting things is the cycle. If you look at this band, this prograde band, this is the beginning of cycle 24, but this prograde band began its latitudeward, the equatorward journey in cycle 23. And even at the end of cycle 24, we see the prograde band that is going to mark cycle 25. In other words, the next solar cycle begins inside the sun long before we see the new sunspots on the surface. The other interesting thing is that the positions of the sunspots where they appear is coincident with this equatorward prograde band, the band that moves towards the equator, which definitely means that when we think about where sunspots form and how sunspots form, we have to figure out how these two are related. Okay. Now, this is a figure where I have shown time on the x-axis and latitude on the y-axis at a given depth. I can show it at different depths, and you can see that the pattern changes. This is what we had seen earlier. This is slightly deeper, 0.95 solar radius. This is 10% into the sun, so 0.9. This is 0.8. You still see prograde and retrograde flows, but the pattern is shifting. You could also look at a given latitude as a function of depth. So this is 15 degrees, 30, 45, 60. So at 15 degrees, you see a prograde flow in the minimum. So 0.8 is below the base of the convection zone. You shouldn't believe much of the results below 0.8 in the sense that the error bars are much larger. But above 0.8, the results are quite significant. So you see the red band, it starts at solar minimum and reaches the surface at solar maximum at 15 degrees. At 30 degrees, however, it's a retrograde band that starts at the base of the convection zone at solar minimum and reaches the solar maximum, reaches the surface at solar maximum. These black lines mark solar maximum. And you could, if you wish, just draw a straight line from here to there, and you'll see the beginning of the next cycle in these data also. So in other words, these flows are intimately related to the solar cycle. The problem is, it's still a bit of a chicken and an egg problem. Are these flows the way they are because of the magnetic fields? Or do these flows affect the magnetic fields? And of course, they're going to affect each other. So what is the feedback? So these theoretical problems are still being worked on. There is no solution. Before I end, I'd like to show you another set of graphs. If you recall, this is again a schematic diagram of solar rotation at different latitudes as a function of depth. This change here is the tachocline, and the tachocline is interesting because we believe this is where the magnetic fields are generated and strengthened. Now, you can define properties of the tachocline, like where is the central region of the tachocline, what is the half width of the jump, but the easiest, the most obvious property of the tachocline is at any given latitude, what is the difference between the rotation rate in the convection zone and in the deep interior? We call this the jump, or delta omega. Jump is easier. So above 30 degrees, the rotation rate is faster in the convection zone than in the deep interior. Above that, it's faster in the deep interior than the convection zone, but you can still define a jump. And if this is indeed the place where magnetic fields are generated, one would think you should be able to detect changes in the tachocline. We've tried this, and we do indeed see a change in the jump, which is latitude dependent. So the red points are how the jump changes at the equator, 15 degrees, 45 degrees, 60 degrees. The background gray is the sunspot number, the axis is on the other side. So you can see, so the first gray bit, the peak, is cycle 23. The second gray bit is cycle 24. And you can see that the changes in cycle 23 and cycle 24 were not the same. At 60 degrees, the jump seems to follow the variation of the cycle, but not at 15 or 45 or at the equator. So what is going on? What is the tachocline doing? Another way of showing this is, instead of showing it as a function of time, I can show it as a function of solar activity. Brown and red is solar cycle 23, which lasted from about 1997 to 2008. The red points are when the solar activity was increasing during solar cycle 23. The brown points are when it was decreasing. The blue and purple are solar cycle 24. And you can see when it comes to the jump, even at the same value of solar activity, so the x-axis is an indicator of solar activity, even at the same value of solar activity, the tachocline behaved differently. So if I go back to the figure of the jump, what is going on? Is it that the tachocline is following not just the sunspot cycle, but the magnetic cycle? I differentiate the two for the simple reason. So the sunspot cycle is roughly 11 years, where the number of sunspots increase and decrease. The magnetic cycle, also known as the Hale cycle, is double that, because what happens at solar maximum, the polarity of the solar magnetic dipole shifts. So if it was North Pole at the north and South Pole at the south, it would shift to South Pole in the north and North Pole in the south. And at the next solar maximum, it would be back again. So the question is this following a Hale cycle? If it were, at the maximum of cycle 25, I would expect this to go down, this to go up, and perhaps this to go down. But we have to wait another 5 to 6 years to see what is going on, if that is the case. Because the other hypothesis is it could actually mean a fundamental change in solar magnetic fields. There was a period in the mid-1600s when, for a period of about 50 years, no sunspots were seen. That's known as the Maunder minimum. And we know that the sunspot cycles have been getting progressively weaker over the last few decades. 50, 60 decades. So are we going towards a very weak cycle? We don't know that yet. I mean, that's why I called my talk Mysteries of the Sun. Okay. And are there changes in structure? Yes, but they're very subtle, so I'm not going to talk about them. We don't quite know. You can see we were trying to look at changes in sound speed, and you can look at the error bars. They seem to be, maybe there's something close to the surface and something here, but we need to look at that. This was with just one solar cycle of data. We need to look at others, so we'll see. But the changes in dynamics are dramatic enough that we've got a lot to think about. So I'd like to leave you with a few thoughts. Although the sun is our nearest star, we don't understand it well enough. Of course, part of the reason is we have so much data on the sun that we don't have on other stars. But we really want to know what the sun is like because it affects us. Even today, the reasons behind the solar cycle and the associated changes are really not well understood. And while the structure of the solar interior is reproduced quite well by our equations, the equations that govern solar structure and evolution, why the interior of the sun rotates the way it does and why the rotation changes the way it does, we still do not have a very good explanation. So thank you very much for your attention, and I'll welcome questions.
Thank you, madam, for your wonderful presentation. So we are sorry that there may be some problem in technical, but it's
That's
very
okay.
great to
That
have been
always happens.
yeah.
Yes,
So, madam, if we allow, we can start discussion. We have got few questions.
of course.
So the first question, what is the sunspot surface?
Okay. If you are asking, so the sunspot surface, I mean, it's nothing really different from the normal solar surface, except, well, that's not true. It is different from the normal solar surface because magnetic fields are inhibiting the transport of energy. There are two things that are happening. Okay. One is the magnetic fields is suppressing convection. So, which is why, you don't see all the energy going out. And we know when we've tried to look at the structure of sunspots through helioseismology, we don't do a very good job. But when we do try to do it, what we find that just below the surface, the sunspots are cooler. And then if you go deeper inside, it's hotter. It seems almost as though there is a heat dam and that hotter part cannot go up. Most of the structure that you see in this figure is basically caused by magnetic fields. We know that the effective temperature, which is the surface temperature of the sunspot, is a few hundred Kelvin, even 1,000 Kelvin at times, below the effective temperature of the non-magnetic regions. This petal-like feature, if you think of it as a sunflower, those are mostly flows associated with the sunspot. And again, the details. So one of the triumphs of the last few years was a beautiful simulation of a sunspot by Matthias Rempel at the High Altitude Observatory in Boulder. It wasn't a simulation, a complete simulation in the sense that he first generated the magnetic fields and then waited for the sunspot to form. What he did is he had a box where he had a magnetic field line. We had magnetic field lines anchored to the bottom of the box. And then he started a simulation using, the laws of MHD. And it was realistic in the sense that the background, the density and the pressure, those were all realistic. And what he ended up at the surface looked almost exactly like this. So these are caused by the normal equations. So it's just the interaction of strong magnetic fields with gas. The bigger problem is actually then what causes those strong magnetic fields in the first place, and how do they get organized, and things like that.
Thank you, madam. There may be a similar question. What are the sunspot and the sun flare? Are they harmful for human in the Earth?
The sunspot themselves are not. The thing is, because the sunspots have high magnetic fields, particularly we see these features in the corona. So you see these high magnetic fields. Let me show this figure. Yeah. So when you have magnetic fields, the magnetic fields can recombine and give out energy. This is what we call a flare. These days, we sort of try and make a difference between a flare and a mass ejection. A flare is mostly the electromagnetic part of the energy emission, where that should not affect us too much. It's the particles from a mass ejection. It doesn't really, it's unlikely to harm life unless you happen to be in the magnetic poles where all the particles can actually reach you. It harms technology for the very simple reason that most of our satellites, let me bring that figure back again if I can. Where is it? Yeah. So as you go above the atmosphere, your protection from the magnetosphere decreases. So things like satellites, which are fairly high above, they can be hit by the particles. And when you have particles in an electronic system, particles are charged particles, so they create currents, which will kill them. Okay. In 1980s, I think, there was a huge particle emission which caused a blackout in the northern part of Canada. So in 2003-ish, is it 2001 or 2003? I'm sorry, I'm sort of blanking on the date. There was a big emission, but thanks to SOHO, we had a sort of advanced warning. Most satellites were kept safe. Only a Japanese satellite, a Japanese television satellite, which hadn't been turned off, right? So it's technology which is harmed more, unless, of course, we have astronauts. So if you have astronauts in the space station who are in the path of these particles, they don't have too much protection because the particles will impinge on the body of the space station and cause a cascade of other particles. And charged particles are bad. They can cause horrible cellular mutations, and it's radiation damage, in other words. Yes.
Thank you, madam. This may be the last question. So, what is magnetogram?
Okay, a magnetogram is simply an image, not of, see, when we think of a photograph, we think of light. A magnetogram is the same image, but of magnetic field. The way magnetograms are taken is basically using the Zeeman effect. So if you remember from atomic physics, what Zeeman effect does is it splits spectral lines or makes them wider. The stronger the magnetic field, the bigger the split is. Okay. So basically, magnetic fields will change the nature of the spectral lines, which allows us to figure out what happens to what the magnetic field is. It's not the easiest of measurements because these magnetic fields that we are talking about, particularly on the sun, are not all that strong. So it causes more of a Zeeman broadening rather than a Zeeman splitting. But the details of how these images are taken, it depends on the instrument itself. They look at the phase of the spectral line, or sometimes they look at the polarization because the magnetic fields will change the polarization. So simply a magnetogram is a magnetic image. Think of a photograph where you're not capturing photons, but you're capturing what the magnetic field is.
Thank you, madam, for your nice presentation and wonderful discussion sessions, madam. So we have just a common question from our student that if any of our student want to do their higher study in astronomy, what she or he need to do, and is there any suggestion from you for our student about that?
To do astronomy or astrophysics,
Yeah.
these days there's really no difference between astronomy and astrophysics. You need a very good background in physics, mathematics. By mathematics, I don't mean pure mathematics, but applied mathematics. So you should be able to. So, for example, if you're doing quantum theory, you do perturbative analysis, you should know enough mathematics to do that sort of thing. These days, I would say statistics, because most of astronomy these days uses very large samples and you need to make statistical analyses. And of course, you have to learn how to code. The current popular coding language in astrophysics is Python. The good news is Python is free.
Yeah.
There's tons of resources on the web to learn Python, and it's quite powerful.
Yeah.
So those are the four things I would say you need. There is a fifth thing which you wouldn't think of, but I think every budding scientist needs to know is how to write well. When I was an undergrad, if anybody had told me that I'll spend more than 60% of my time writing, particularly as a senior scientist, I wouldn't have believed them. So learning to write well matters. And I don't mean write in a flowery literary language, but write precisely so that everybody knows exactly what you mean. And then if you have energy, you need to learn how to give public presentations, because your jobs are going to depend on, giving an interview and particularly giving a talk about your work. So the science is physics, chemistry, statistics, you have coding, and you have learning to write and learning to speak.
Thank you, madam, for your nice suggestion. So thanks again for accepting our invitation and giving us time in this corona pandemic situation for our student. So we'd like to say thanks again on the behalf of the Department of Physics, Pabna
It was
University
my
of Science and
pleasure.
Technology.
It
Yeah,
was
it's
my
we
pleasure.
are we are very proud actually to host you, madam, and it's my pleasure actually to host you. So thanks again. Good night and have a nice day to your part. And
Thank you.
hopefully in near future we will arrange another webinar with you, and after the COVID and when you will visit your country, so I'll definitely invite you to visit our country also.
I shall remember that.
Yeah.
Yes.
Bye
Okay.
for today.
Bye-bye.
Thanks. Bye.